Okay, everyone, in this video, we're going to go over the first half of Chapter 4's information. This is going to be a lot of information about learning about atoms and elements. We're going to go through about the first half of the bullet points here, where we're going to start to be able to recognize that all matter is composed of atoms. We're going to be able to explain some of the experiments that led to the discovery of the atom as we think about it today. And then we'll talk a little bit more about those models that describe the way we think of atoms today. So just a reminder, as we've talked about before, all matter is anything that has volume and has mass. So anything that has those traits is going to be made up of atoms. So in this chapter, we're going to start to get more specific about what we mean by atoms, give you an idea of what that is. However, there are about 91 naturally occurring types of atoms, or elements, as we'll continue to call them. And what I mean by this isn't that there are 91 atoms on the periodic table, because that's obviously not true. There's up to 118. However, as we know so far. However, there are 91 that we can naturally occur with and interact in our environment without having to make them in a lab somewhere. And as you can see, speaking of in a lab somewhere, now that we know a little bit more about atoms, we're able to do cool things like manipulate them and stuff like that. So this is a surface of xenon atoms that IBM went out of their way to write their logo in literal individual atoms. So some of the cool stuff we can do with this science, at least. So what's important here to know is a little bit about the history of the atom. We got to kind of know where we came from to know where we're going. So the first people to conceptualize the idea of atoms were the Greeks. They had a word called atomos, which meant indivisible. So they thought of tiny indivisible parts of matter. So they knew you could cut matter up, but what they're saying is at some point you can't cut it up anymore. You're going to get to a stopping point. So that was their thought process there, and they called those littlest pieces you could get atomos because they were indivisible once you got to that point. As they were presenting these ideas, of course, as often happens in science, they were not very widely accepted. So it sat on us for hundreds of years, these concepts from the ancient Greeks, up until we meet John Dalton. I don't have offhand what years John Dalton lived. I believe he's closer to the 1800s, if you want my opinion. 1800s, so over 2,000 years later is when Dalton finally came in and formalized the idea of an atom. So he saw what the Greeks said, hey, let me actually make a theory out of this. Let me write it down. Let me give it a formal definition. And so once Dalton introduced this idea, it became a bit more accepted and more about what we know as atomic theory today. So Dalton formalized the concept of an atom. He wrote atomic theory. So his atomic theory states that each element is composed of tiny, indestructible particles called atoms. That was that idea up there from the Greek atomos. But he also theorized that all atoms of a given element have the same mass, and that they have other properties that distinguish them from atoms of other elements. So if you have an atom of gold, for example, you should very easily be able to tell that apart from an atom of silver based upon the mass and some other properties as well. His third point was that atoms combine in simple whole number ratios to form compounds. So basically it's reiterating the idea that we couldn't take a part of an atom and put it into a molecule or a compound or something. That doesn't make sense. We're not going to have like 3/4 of an atom or something crazy. We're talking about whole atoms, and when we combine them, that means they get combined in whole number ratios to each other. We're not, again, splitting atoms. So we continue to find evidence to support these ideas of the atomic theory, just like IBM was able to use, in the end, atomic theory, knowing that there were each individual atoms there. They used that theory, and a lot of other science, obviously, to be able to drop their little letters to make their IBM logo. So we're still using atomic theory to this day. It's still being studied, and they're still finding evidence for it today, and we're still applying it in many different ways. So it's not going away. It's still hanging around. So the thing is like once we had this concept of an atom, we kind of had to do something with it. So, we didn't really know what it was. The Greeks kind of thought it was like a hard sphere. So it was a solid sphere made of whatever material it was. Dalton, I think, kind of had the same idea going, that it's got to be some sort of sphere with stuff because it's matter. It's got to have stuff. It's got to have mass, right? So the thing is, more scientists came along and more scientists did some experimentation, and it's going to lead us into the idea of a nuclear atom. So when we think about atoms, a lot of times we have in our head like the Jimmy Neutron logo. You've got all little things in the center, and you've got these big loops of stuff flying around the outside. Whenever you think of like nuclear symbols, for example. Usually I have something like with a logo of this with an arm reach because I worked at the nuclear plant, but it doesn't look like I have anything there right now. But that's kind of the idea that we have in our head. So we're going to figure out kind of how we got to that idea. So we're going from a solid ball to there must be a lot of mass in the center and some stuff around the outside. So let's figure out where we went from and where we're going to get there. So the next guy that steps in our tale to kind of do some experimentation is J.J. Thomson. So J.J. Thomson is a pretty cool guy. And basically what he did was he basically looked at some atoms, looked at the way electrical current worked, thought about it, and he used 2 electrodes to create a stream of particles that he knew he was breaking off from atoms. Wait, didn't we just say that atoms were indivisible? Interesting. So he's figuring out that atoms are made up of smaller particles than what we may know. So he was able to have this stream of particles. And he was able to set up that stream of particles and then bend that stream of particles. If he introduced like a negatively charged magnet, for example, he would see that those particles were being repelled by the magnet. Interesting. So basically what he discovered is that there are electrons. So there are tiny little negatively charged particles that reside within atoms. He figured out that they were negatively charged because they repelled the negative end of a magnet. And he used this evidence to change the conceptualization of an atom, right? So we were thinking of an atom as a solid sphere. However, it can't just be a solid sphere if I can break something off of it. So what must it look like? The idea he came up with is what we call the plum pudding model. So the plum pudding model. I know it sounds great. So the idea is that there's this sphere of positive charge with all these teeny tiny little electrons dotted throughout that sphere of positive charge. And so they've got tiny little electron particles in a sphere of charge. So it's kind of like having the plums be electrons and the pudding be that positive soup around the outside. So you've got a pudding kind of cloud with some electrons in it. So that's kind of how we can think about a little bit how the model works. So you got just a sphere of positive charge, so an empty volume of positive charge filled up with all these little teeny tiny dots. That's what he came up with. He said, okay, I know there are electrons. I know they must be there. Sphere of positive charge with some negative electrons in it. That's where J.J. Thomson left us. Oops. So then Rutherford comes along and he says, okay, great. Plum pudding model of an atom. Sounds awesome. I'm in. I like this idea of these new electron things. However, he was like, I think we could do some more experiments to confirm if this is the model. Let's look for some more evidence. Let's continue to prove that this is what we think it is. So what he did was he set up an experiment to confirm the plum pudding model. We call this the gold foil experiment. So all he did was he directed these very small particles called alpha particles at a gold foil. Well, if atoms were really this sphere of positive charge, this empty volume of positive charge with just these little teeny tiny dots of negative electrical charge in it, those electrons, then those alpha particles are just basically going to pass right through that all the time. Those electrons, they're kind of floating around. They're not really going to get in the way. There's not a lot of space they're taking up. They're not huge. They're not really going to get in the way. So what they expected to see is if they shot alpha particles at this piece of gold foil with a detector surrounding it, basically they figured they'd just almost always see their alpha particle there on the back wall. Shooting particles, it's just going to go straight through my foil. I think atoms are mostly empty space with just a little bit of electron in them. Okay, we're going to go straight through. They're going straight through the foil. However, some particles did this. But Rutherford and his grad students were super thrown off guard because what actually kept happening was that the alpha particles were deflecting back at really weird angles all the time. They were hitting something and deflecting back, hitting something, deflecting back, hitting something, deflecting to the side, hitting something, deflecting just a little off, right? They weren't going straight through the gold foil like they expected without having some sort of interference. They had some sort of interference. So basically, therefore, Rutherford said, plum pudding model must be wrong. I'm not getting what I expected. What else might be in the way? What might be happening here? What can I come up with that could describe the situation better than what the plum pudding model is? So what Rutherford came up with is what we call the nuclear atom. So you can see in the first picture up here, if we had the expected result. So again, Rutherford thought he was going to prove the plum pudding model correct. He expected all the alpha particles basically to push through and not be interfered with. However, they were interfered with. So he said, okay, if we have the plum pudding model, there's nothing to interfere with them. However, we're seeing some sort of deflection, some sort of interference. This is more what he conceptualized an atom to look like. There must be some mass there in the center that's keeping them from passing through all the time. There must be a lot of empty space because they're passing through the gold foil quite often. They pass through the gold foil more often than they are obstructed by whatever is there. However, every now and again, those particles are obstructed. So there must be something there to obstruct them. So he decided to call this the nucleus, and he theorized there must be a nuclear center to the atom where there's a very dense area of matter. And he called that the nucleus. So the nucleus would be the center of the atom with lots of empty space around it. So he thought, this describes my experiment. Often the alpha particles are passing through my gold foil, hitting the back of the detector where I expect. However, every now and again, they're bouncing off and hitting places I don't expect. He believed that this model could help describe the way his experiment happened. And to this day, we still stand with the nuclear theory of the atom, therefore. So the nuclear theory of the atom is more specifically about the way an atom is set up and the way we think about an atom kind of being set up and put together, whereas the atomic theory says that atoms exist. Nuclear theory says this is what we think atoms are made of, kind of a deal. So Rutherford therefore developed the nuclear theory of the atom once he figured out that he wasn't actually proving the plum pudding model correct. He was putting, he was going to put his own idea forth. Therefore, if the plum pudding model wasn't correct, this is what an atom is. This is the nuclear theory of the atom. So when Rutherford put out the nuclear theory of the atom, what he said was, point one, most of the atom's mass and all of its positive charge are contained in the small core in the center of the atom called the nucleus. Most of the volume of the atom is empty space through which the tiny negatively charged electrons are dispersed. So he set it up that all the positive charge and most of the mass are in the nucleus in the center of the atom, and most of the volume is taken up by space for the electrons to fly through. So those negatively charged electrons are flying around the outside of our atom. And in the center sits a lot of mass that contains all of the positive charge. The third point here says there are as many positively charged particles inside the nucleus as there are negatively charged electrons outside the particle, so that it is electrically neutral. So the idea here is that in a neutral atom, in an atom that contains no charge, what you must assume is that it has just as many positives as it has negatives. We're going to talk a lot more about electrical charge in just a second here. However, it's just a part of the nuclear theory that if there are just as many positively charged protons as there are negatively charged electrons, then you have a neutral atom. So lots of scientists have contributed beyond this point. So we do have models of the atom that go further than the nuclear theory of the atom or the nuclear model of the atom. We have scientists who came in after Rutherford who have done lots more things. So this is kind of some of the stuff I was studying in grad school would be along the lines of like thinking about the nuclear theory of the atom and stuff like that, what we conceptualize atoms and electrons to be. However, for our purposes, we can leave it with the kind of idea we get of an atom after Rutherford has left us with the nuclear theory of the atom. So what does this look like? We might call this the nuclear theory of the atom, like the model or the nuclear model of an atom. So a nuclear model of the atom is going to look something like this. So you would have a dense center of the nucleus where your protons and neutrons are located. We'll talk a little bit more about protons, neutrons, and electrons, what we call subatomic particles, in just a second here. But what you need to know is that, again, 99% of the atom's mass, almost all of the mass, is contained in this dense small nucleus space. And then we've got all this yellow space around the outside that represents a large empty volume. However, that space where those electrons can fly through and be kind of almost contained in, even though they're not like kept in place or anything, they're just flying around the outside. So they're kind of the volume of the empty volume of the atom is just where those electrons might be, kind of a deal. So electrons around the outside in a mostly empty space, all of that positive charge, most of the mass in here in the center of the nucleus. So that is kind of the history of where we got the atom from, a little bit about atomic theory and a bit about nuclear theory. So after this, I'll upload in a video just a little bit more about those subatomic particles and then how we can start to identify atoms as elements and tell them apart from each other.